Welcome to this explainer. Today, we're going on an absolutely mind-bending journey into one of the most fascinating concepts in all of mathematics and physics, the fourth dimension. Whether you've heard about it in your favorite sci-fi movies or stumbled across it reading about theoretical physics, the fourth dimension challenges the very limits of human imagination. We're going to break down exactly what it means, both mathematically and physically, and by the end of this, I promise you're going to see the universe in a completely new way. Okay, let's dive into this. We live our everyday lives in a three-dimensional world. Basically, everything you see, touch, and interact with has length, width, and height. Our brains are entirely hardwired to understand reality through these three directions. So the fundamental impossibility we face right out of the gate is this. How do we even begin to visualize a dimension that exists completely outside of our everyday experience? It's a massive puzzle, but one that's fascinated mathematicians, physicists, and artists for well over a century. But hey, don't worry, we've got a really clear map for our journey today. We're going to cover beyond our 3D world, building the tesseract, time, the fourth dimension, bending spacetime and gravity, and finally, pop culture and beyond. We're going to tackle both the geometric shape and the literal physical reality of time. Let's start with Section 1, Beyond Our 3D World. To truly understand the fourth dimension, we first have to recognize the limits of our own three-dimensional brains. To completely validate why you, or anyone, might struggle to picture higher dimensions, we just need to look at a brilliant 1884 novella called Flatland by Edwin A. Abbott. Imagine a world that's perfectly flat. Two dimensions, just length and width. The beings living there are literally flat squares and triangles. If a three-dimensional sphere were to drop down and pass directly through their flat world, they wouldn't see a sphere at all. Because they lack any concept of up, they would just see a 2D circle that magically appears out of nowhere, grows larger, shrinks, and then completely vanishes. They are entirely blind to the 3D reality of the object passing through. Well, guess what? We are just like those flatlanders. Because we're 3D humans wired for a 3D universe, we simply cannot perceive a four-dimensional object in its entirety. If a 4D object were to pass through our three-dimensional space, we wouldn't see it as it truly is. Instead, we just see a morphing, shifting 3D shape. Basically, it would look like a 3D shadow or a single slice of a much more complex 4D reality. Let's move to Section 2, Building the Tesseract, and see how this builds. So how do we get from an abstract mental block to a concrete geometric construction? I'm going to guide you step by step right up the dimensional ladder. You build dimensions by taking a shape and sweeping it in a perpendicular direction. Let's start with a single point. That's 0 dimensions. Drag it out, and you get a 1D line segment. Take that line, drag it in a perpendicular direction, and you sweep out a flat 2D square. Take that square, and pull it directly up into a third perpendicular direction, and boom, you've got a 3D cube. Now to get to the fourth dimension, you take that cube and move it along a fourth perpendicular direction, a direction we literally cannot point to in our physical space. The resulting mathematical shape from that movement is a tesseract, which is also known as a four-cube. The math behind this shape is absolutely wild. Just like a standard 3D cube has 6 flat faces, the hypersurface of a 4D tesseract is made up of 8 entire cubes. It's got 24 square faces, 32 edges, and 16 vertices. And you know how you can unfold a cardboard box into a flat 2D cross on the floor? Well, you can unfold a 4D tesseract down into 3D space. There are actually 261 distinct ways to unfold it, and one of them results in a 3D stack of 8 cubes known as a dolly cross.
So the crucial point is, we need to draw a hard line here. Up until now, we've been talking entirely about geometric 4D, a theoretical shape with 4 spatial axes. But in physical reality, the literal fourth dimension we experience isn't a spatial direction at all. It's time. This is where we transition from the pure mathematical geometry of hypercubes into the physical reality of Einstein's spacetime.
That brings us to Section 3, Time, the fourth dimension. Let's shift gears to theoretical physics, where time isn't just a separate ticking clock in the background, but a fundamental fabric woven directly into space itself. Early in the 20th century, scientists like Hermann Minkowski and Albert Einstein revealed a really profound truth. Time and space are not separate stages where the universe plays out. They are unified into a single, continuous thing known as space-time. If you want to accurately pin down your location in the universe, it's not enough to just give your 3D coordinates, your length, width, and height. You also absolutely have to give your position in time. The 4 dimensions work together constantly. And because time is dimension, it's relative. It's not this absolute rigid thing. It's incredibly malleable. According to Einstein's theories of relativity, the speed at which you move through space actually affects the speed at which you move through time. Plus, because of this mind-blowing phenomenon known as gravitational time dilation, time actually passes more slowly the closer a clock is to a massive gravitational object. Time literally bends. Moving into Section 4, Bending Space-Time and Gravity. And this brilliantly illustrates exactly how that bending works, showing the mechanics of how massive objects interact with this four-dimensional fabric. To picture this, imagine 4D space-time as a stretchy trampoline fabric. If you place a heavy bowling ball, representing a star like our sun, right in the middle of this fabric, it causes a deep dip. If you roll a smaller ball, like a planet, nearby, it naturally circles and rolls toward the dip. It isn't being pulled by some invisible, magical force. It's simply following the natural curve of the space it's moving through. This means gravity is quite literally just the geometry of curved spacetime. To ground this high-level theoretical physics in everyday reality, we just have to look at our GPS systems. The clocks we have down here on Earth are sitting deep in Earth's gravitational curve, so they tick just a tiny bit slower. Meanwhile, GPS satellites orbiting way up in space are further away from Earth's gravity. But they're also moving at incredibly high speeds. Because both gravity and speed warp the fourth dimension of time, these satellite clocks run at fundamentally different rates than the ones in our phones. If scientists didn't constantly, mathematically correct for this real-world time dilation, our GPS systems would become useless in a matter of minutes. This 4D space-time fabric makes some incredibly extreme cosmic phenomena possible. Because space bends, light itself actually bends around massive objects. This is a phenomenon called gravitational lensing, which was famously observed by Arthur Eddington during a 1919 solar eclipse. It's also the mechanism that creates black holes, which are regions where space-time curves infinitely deeply. And mathematically, it even allows for wormholes, hypothetical tunnels through space-time that could act as shortcuts, connecting two completely distant regions of the universe instantly. Let's wrap things up with Section 5, Pop Culture and Beyond. With scientific and mathematical concepts this wild, it's really no surprise that they've leaped out of the laboratory and totally inspired the art and media we love. The deep science we've been discussing is the DNA of some incredible pop culture touchstones. In literature, authors like Robert Heinlein wrote classic stories about buildings literally collapsing into folded tesseracts. Salvador Dali painted Jesus on an unfolded hypercube in 1954. Today, Marvel's Loki series deals directly with branches and loops in the 4D timeline, echoing actual multiverse theories. And the movie Interstellar, which by the way was actively advised by theoretical physicist Kip Thorne, breathtakingly portrays both gravitational time dilation and the mind-melting concept of navigating a five-dimensional space.
Now, what's really interesting about this slide is that physics didn't just stop at 4 dimensions. Modern string theory suggests that to unify all the forces of nature, the universe might actually be constructed of up to 11 dimensions. These extra spatial dimensions are theoretically curled up so incredibly tight that we simply can't see them. Some theories even suggest that hypothetical particles called gravitons, which are basically particles of gravity, might actually be leaking or traveling between our 3D world and these other hidden dimensions. And that might be exactly why gravity appears so incredibly weak compared to the other fundamental forces of physics.
It completely shatters how we view our place in the grand scheme of the universe. We started today as simple flatlanders, right? Unable to even see the higher dimensional shapes around us. But we learned to stretch our minds mathematically to visualize the tesseract, and physics showed us that our every movement is literally a dance through a 4D space-time fabric. So I want to leave you with this thought. If string theory's 11 dimensions are actually real, what else is hiding just beyond the limits of our perception? What other incredible realities are passing right through us right now, casting shadows we just haven't learned to see yet? Thank you so much for joining me on this explainer. Keep wondering and keep looking beyond the surface.